ship to another would communicate to another ship using movements of the arms, movements of the legs, and maybe the use of flags, and maybe the use of coloured flags. And of course, in those days, they didn't have electronic communication. Certainly in the 18th century, they didn't. And the only way that ships could communicate at sea is by means of semaphores. So we're going to have a look at the computer science equivalent of semaphores in a moment. So anyway, I'm just going to unload my presentation. That shouldn't take too long, hopefully. And I'll tell you when it started. And there is actually one other remark I'd like to make, and that is, if you're in the habit of downloading files from Moodle, as far as the files on Moodle are concerned now, wait until some of them have been updated, and I've added a couple of files to those. So don't, just take your time in downloading those. Okay, so let me see. Let's see where we are. Okay, here we are. I think this is it. I'm uploading it. And I found that if I talk for too long, the recording breaks, so I have to sort of record it again. So probably we'll have a little bit of a break in about an hour's time. So, okay, this is the presentation, and this is the word semaphore. Okay, it's a semaphore, and I'm going to define what we mean by a semaphore in computing. Can you see that? Can you all see that? Okay.
Yes, sir.
Thank you, Hassan. Okay. Okay, so definition of a semaphore. Why do we need them? Well, they're very, very useful to get synchronization between two threads or two processes or two machines or two people. What semaphore is a special variable, and it's a binary variable. In other words, a semaphore S can only either be hold the value 1 or hold value 0. And the way in which a semaphore is implemented is that you have a single shareable memory cell containing 1 bit, so it's a 1 or a 0. And it's special also, not only because it can only be 1 or a 0, but because it supports 2 operations. So there are 2 things you can do with a semaphore. Either you can perform a wait operation, and I'll tell you what that is in a second, or you can perform a signal operation, and there's converse operations. So here's the definition of a wait operation, and in a sense it's quite straightforward. So definition of waiting on a semaphore S is this: is while S is equal to or less than 0, don't do anything. The only thing you might do, because you're not doing anything useful, is to ask the operating system like Unix or Windows 10 to block me and to wake me up when the value of S actually changes. Because the process responsible for changing the value of S will issue an operating system command saying, please tell all the other processes or threads that there has been a change in circumstances. S has changed value. So, okay, so while S is less than 0, less or equal to than 0, don't do anything. I mean, you don't need to do anything, just don't do anything. But when it changes when S changes from 0 to 1, then I'm immediately going to decrement S by 1. In other words, set S to the value of S minus 1, decrement it by 1. Okay, that's the definition. And okay, so in some sense, it's if you execute a wait operation, you are literally going to wait until the value of s becomes 1. When it becomes 1, in other words, it's giving you permission to do something, you immediately decrement it. And the idea here is that you're telling everybody else that you are busy using a non-shareable resource. You are the guy who's sitting on the chair. Nobody else is allowed to come along and sit on the same chair at the same time. Okay, so the wait operation is forcing a process to wait whilst any other process is busy using the resource. And if nobody else is using the resource, the value of the semaphore will be 1. And I change it to 0 to warn other people off. Okay, so hopefully that's reasonably clear. Definition, a second definition, okay, a third definition on this page. Definition of a signal operation is this. It's just to simply take the semaphore S and add 1 to it. But in addition, you're going to notify, this word is notify all. You're sending a signal, I think, to the operating system saying, please wake up all the blocked processes, the processes that are waiting for something to happen. Wake them up. So, for example, if this process, the process that's executing wait S, is actually blocked, it's not doing anything on the CPU, then the operating system comes along and says, wakes it up, so it wakes up, and if it checks the value of S, if it's 1, it changes it to 0. Why? Because it wants to use what's called the critical resource, the unshareable resource, logically non-shareable resource. So what notify does, little note here, is wake up the first process or thread on the waiting queue. And with these two fairly simple operations on a semaphore, we can implement a strategy or a mechanism for ensuring that Chris Kenberg does not do anything dangerous. He doesn't try and grab a non-shareable resource when it's in use. And we discussed, I think we discussed this idea very, very briefly last time we met. Anyway, there's another definition of a wait, and I might as well give you this. And it doesn't involve asking the operating system to put me in a queue, which, in other words, put me to sleep and then wake me up when there's been a change in the value of S. This is very straightforward, but a very inefficient way of defining the wait operation. And it's this: while S is equal to or less than 0, do nothing. Look, I've got a 2 bracket here, nothing. As soon as I've woken up, set S to S minus 1, decrement it by 1. And it's called a spin lock, because I'm just, 100,000 times a second, I'm checking the value of S. It's sometimes called a busy wait. I'm very busy, but doing nothing. All I'm doing is to check the value of S again and again and again. Probably many thousands a second. It's very inefficient. It's a waste of CPU time. That's why in some operating systems say, look, all you have to do is to ask me to block you, and I will, and I'll wake you up when the value of S changes. So hopefully you understand a little bit now, because we've had one session on non-shareable resources, and the fact that people cannot pass through a narrow doorway at the same time without really hurting one another, and two people logically cannot share the same pair of spectacles at the same time. You can't share your left eye either. You can't share the space in which your left foot is occupying. You can't do it. Somebody else can't come along and put their foot in the same space as being occupied by your foot. You'd get a very nasty breakage of foot bones if somebody tried to do that. And physically it's not possible, and probably logically it's not possible to share space. Nobody can occupy the space that my body is occupying, and so on. So what I'm actually saying, and hopefully I'm giving you a suggestion, is that the world is full of non-shareable resources. But for most of the time, we're not really aware of them. But if you think about it, if you think about the hazards of crossing a word, sorry, I'll say that again. If you think about the hazards of crossing the road, I'm going to get, I'm going to get seriously injured if I and the motor car that's coming towards me attempt to share the same space. I'm going to get very bad. The car's going to get injured too. So attempting to share a non-shareable resource is very dangerous at the best of times. And in fact, when a computer crashes, it's usually because one process or one program is attempting to use a resource that's actually already in the possession of another process. And I'm thinking of something that's absolutely trivial. It's like if I and you attempt to write different binary digits to the same memory location, we're in trouble, because only God knows whether the result of you and I trying to write 1 and a 0 to the same memory location is going to result in garbage or a 1 or a 0. There's no way of telling. No way of telling. So it's serious. And the one might be represent the fact that aircraft number 3 can actually land because aircraft number 1 has actually taken off and the runway's clear. So it's quite serious. It's quite serious. So what I want to discuss now is something called the producer-consumer problem, and it's a rule. It's a fact, but it's a rule of the world, how the world arranges itself. And I'm including things like hardware processors, software processors, firmware processors, wetware processors, real life things, things in the world often arrange themselves in the following relationship. One of the processors is going to be a producer of something, and the other process, and I'm just assuming for the time being that there's one producer and one consumer, and it's a very distinct relationship which creates certain problems that we need to be able to solve in computing. And a very simple, basic example of the producer-consumer relationship is something I think I've mentioned before. It's a cook, i.e. a chef, working on his own, and consumer, somebody who walks into his eating house and says, "Can I have, can I have a meal?" And other things being equal, the producer, the cook, can actually spend 20 minutes making the consumer a meal, and the consumer will consume it. But what happens? There's a problem if the producer is just a single producer, and then 10 different consumers all come in at more or less the same time and saying, "Can we have meal A and meal B and meal C and so on and so on." 10 different meals maybe, or 5 different meals. 10 meals. And the producer's going to have to say, "Look, I'm sorry, but it takes me about 10 minutes to make a meal." The 10th consumer is going to tell, "Well, look, it's going to take 10 times that amount of time, you're going to have a long, long wait. And therefore, one or more of consumers are just going to walk out of the cafeteria or the eating house or whatever it is. They're going to be very dissatisfied. So, on the other hand, maybe the producer's actually been very busy and he's making meals very, very quickly. So maybe it's a fast food Mexican restaurant. All he has to do is to reach into this tub to get some refried beans, and he puts them in between. I can't remember what the Mexican taco, I think it is. Puts it in a taco, and it's ready. It's done. Very quick. So maybe, but on the other hand, maybe the consumer has got a huge appetite. He weighs 160 kilograms, and he can eat enormous amounts of food, and he often wants a double helping, a second meal. His reputation is the world's strongest man, and he needs to eat a lot. Okay, well, what happens? The consumer can actually probably outpace the rate at which the producer can produce these Mexican tacos. In other words, there's something that, I hate saying this because it's a technical description, but maybe the bandwidth of the consumer exceeds the bandwidth of the producer. Or it could be the other way around. The producer can't keep up with demand. So the bandwidth of the producer is much less than the bandwidth of the consumer or consumers. And in each case, there's a serious problem. Because, I think the producer, the chef's credibility is at stake. This eating house can't give you food within 2-hour limit, or and so on. So what does bandwidth mean? I just mean the rate at which things can be made. Bandwidth. We've spoken about the bandwidth of a CPU. The bandwidth of a CPU is the rate at which it can execute instructions. Okay? The bandwidth of a memory is the speed at which it can output data that's being read from the memory. So we've got a bandwidth problem, bandwidth mismatch problem between CPU and slow memory, maybe. And we've seen how to solve that. We've used the cache memory to solve that. But what I want to say, I want you to think about this. This general relationship between producers and consumers. In a sense, I could say, look, I'm playing the role of a teacher, and you are playing the role, whoever you are, you're playing the role. What was that? I've just seen a note from Abdullah, which I don't quite understand. But can you all hear me? We haven't got that problem again, have we? Anyone? Is anyone there? Hussein? Can you hear me, Thorhad?
Yes, sir, we can hear you.
Okay, it's just Abdullah can see visual single flash flags, and I don't know what that means. Anyway, everything's okay. I'm gonna continue. Okay.
Okay.
So I want you to think very seriously about this general kind of relationship that things in the world might be. It might be your relationship to other people, or it might be one of your friends might be a farmer who's producing potatoes or corn or olives or whatever, and you are a literal consumer. You go and buy his olives once a week. I produce a consumer. Maybe the example was I'm going to lend people money, and maybe I'm a sort of like a producer of instant wealth, and you, the consumer, are going to borrow money if it's okay, if you need to, for a definite need. Okay, so think about it, and I'd like you to perhaps come up with a list of 5 different producer-consumer relationships. But what I do know is that inside some intuitive examples of this, cooks and diners, well, I've covered that. Multipliers and algorithms, that might not make much sense, but some algorithms repeatedly make use of the results of multipliers. They need 2 numbers multiplying. So a particular way of calculating something might require the specialist use of a multiplier on the computer. And that's a perfectly good example of a producer-consumer relationship. Okay, teachers and students. What about web clients and web servers? You know, I'm a client of a web server that tells me, you know, what the weather is like in my home country of Sweden every so often. I get worried about the melting Arctic ice cap, and sometimes get worried about the condition that reindeer are in Tuami in northern Sweden, and so on. And CPU modules and memories, client server. And believe it or not, each bus you have inside not real buses, omnibuses, I'm talking about buses in a computer, has an associated bus driver. In order to I can't remember which way round it is. I mean, I suppose a bus needs to serve services of a bus driver. It's a bus wants to route data in such and so direction to such and so device. Well, the bus driver will help the bus transfer data from A to B. So that's another not so good example, and I'm sure you can think of much better examples. And so I'm going to now talk about buffers. And if you remember, it's a bit of a vague word. What a buffer is, it's just a little bit of memory. It's like a slot of memory into which a computer can store data temporarily. And the reason I'm talking about buffers at the moment is that they play an important role in, firstly, this you might come as a surprise, implementing asynchronous communication. And I'll explain that in a moment. And secondly, in solving any bandwidth mismatch problem where producers and consumers need to interact efficiently whilst producing producing some kind of product X and consuming the product X. I mean, ideally, you know, the rate at which a producer can produce is going to be the same rate as the consumer consumes. But we're going to have a look at the use of a buffer to ensure a solution to that problem. Well, just let's remind ourselves why B is a problem. Well, I mean, maybe I've got a producer that's capable of producing a huge amount of maybe data, maybe food, maybe whatever you want it to produce. And on the other hand, the consumer might be very slow in consuming data or the food or whatever. And it seems a shame that this productive producer has to close down, shut down. You know, there's some kind of lockdown. You know, you mustn't produce anymore, can't handle it. Too much data. Can I give you... oh no, okay. Well, let's return to A here, implementing asynchronous communication. Let me explain this in the model of the post office, British Post Office. If you want to communicate with someone in Scotland, you've got one way of communicating asynchronously is by writing a letter and addressing it correctly and putting it in the letterbox. postbox. And maybe if you're lucky, 3 days later it'll arrive in Edinburgh. I think that's the capital of Scotland. And the point about that communication is that I've sent the communication, I've sent a letter, and now I can forget about it. The job's done. And when the letter is delivered at, say, a young lady's letterbox, she can actually take the letter and read it when she wants to. She doesn't have to read it straight away. Okay, so this is called asynchronous communication. I can send a communication or data or send a conversational recording at any time I want. I don't have to do it by the clock. You know, I don't have to suddenly say, look, now's the time I've got to send it. I'm just going to do it. Just going to send it when I want to. Post the letter when I want to. It can be midnight. But the communication will get to the addressee problem. And I can contrast that with synchronous communication. Again, using, I guess, a British telecom by saying, I want to make a phone call to this person in Edinburgh. What I need to do is to dial her number and wait until a connection is made. Now, there are two possibilities. A connection isn't made, in which case communication isn't possible. And the other possibility is that, yes, she picks up the phone and you know, in effect, agreeing to take the call. Well, that's fine. But it's synchronous communication. It depends on our synchronizing our activities. Why? What do I mean? Well, I mean, first of all, she's got to be ready to communicate. She's got to pick up the phone. If she's there, she pick up the phone. To start with, I've got to actually dial a number or press buttons on my iPhone to establish the call. So there are two fundamentally different ways of implementing or modeling communication. One is asynchronous communication, and the second is synchronous communication. And as far as asynchronous communication is concerned, I can establish it by the use of a buffer. Okay, that's what I want you to remember and to think about, and I'm going to give you a little bit more detail. So here we go. I think, right? I mean, slide 7. Okay, so no, I haven't moved on yet. Go. Right. So I've given you a little note of A and B, I think. And the idea is, I mean, let me explain the idea of establishing asynchronous communication. Suppose it's communication between two hardware devices, and I want A to communicate with device B asynchronously. One way in which I could do that is to simply have an array of vacant memory slots. I mean, maybe I've got 10, and I can fill that with 10 bits of data. And so logically, what I could do is to put a bit of information in the 10th, then the 9th, 8th, all the way to the 0th. Okay, and I couldn't care less whether device B is actually going to receive that data right now. I couldn't care less. I've done my job. I've actually sent the device B a message, and it's up to him to read the message. So it's asynchronous because I don't have to synchronize with him. He doesn't have to be ready to read the data I've sent him. Right, so that's the key idea. And you might think, well, it's quite simple. I'm going to do a little experiment now, and I'm connecting you up to a very, very high frequency sound. Yeah? Just listen out for it. And tell me what I've said. Okay, so I reckon that high-speed signal lasted about probably a quarter of a second, but it contained 30 megabytes of data, and I was transmitting the data very, very, very quickly. And in fact, what you've just heard was a bit of sound, a bit of a signal coming back from a deep space probe, compressed data. Let me ask you a question. Did you understand what was said? Right. I mean, hopefully you heard it, but on the other hand, I think it was quite a rapid transmission with a lot of data, and I reckon that there is no way on earth that any one of you could remember what I've just transmitted to you. It's too much data for a start, and too small a time period. It's done very, very, very quickly. Hey. So if you wanted to solve that particular kind of communication problem, you've got to enable some kind of buffer to keep the data that you've just received safe. And maybe it's going to take you 3 days to the data byte by byte, or maybe 10 bytes per unit time. But you've got to buffer it. Otherwise, I mean, if I this might be happening now. If I speak to you and you're not listening, the data's gone. Can you hear me, Hussein? Every time I see a little message from Hussein, I think, oh no, he can't hear me. Can you hear me? Well, I'll wait until you type a message in. But hopefully that's given you a couple of ideas that may be worth thinking about. So the two models, as I said at the beginning, was sending a letter, you can send it at any time. On delivery, on delivery, the receiver, it should be, can read the letter at any time they choose. And the different model is making a phone call. Communication can only take place when the call has been established. Oh, Hussein! Alright, so anyone... wait a minute.
Yes, I can hear you.
Okay, so I think it might just be Hussein. Hussein, could you log out and log in again? Thank you, Abdul Rahman. Lots of very fast responses here. So I'm going to carry on, and hopefully...
I can hear you, sir.
Hassan, are you alright? Can you hear me?
I'm
Thank
good.
you. Good to hear your voice. I'd much rather see your faces, but I think if we have webcams on, that's just going to, I don't know, it's going to load the system a little bit.
Oh, no problem. I'm willing to do both, whatever you like, Mr. Chris.
Okay. Torhath. Well, I'm just going to carry on, but I'm keeping a lookout for people saying I can't hear. Right. And I hope you can. And remember, if you can't hear and there is a gap in the recording, then if the recording fails, which has happened on 2 occasions before, I'll take steps to make a duplicate recording. But it might not be as fun as to listen to as the original. All right. So, okay. Well, I'm just explaining a little bit about problem to do with B, with some kind of mismatch. And okay, Hussein's signing out and signing in again, so I hope he's okay. Okay. And I'm not going to sort of duplicate that, but it's well, there's a bit of a problem. I mean, supposing, um, another example is a producer who produce one meal every 2 hours because it's for a wedding. It's a special meal. So it takes them a long time to produce a meal. What happens if on the Monday, the beginning of the week, he's expecting to serve 100 people lunches? I mean, it's a real problem. It's a real problem. And it arises again and again and again, not just in electronics, but in the real world. Oh, one idea is that if he can cook each meal and keep it fresh somehow, maybe he's got a special semi-chilled cabinet in which he can keep many tens of meals. I mean, maybe that's a possibility. On the Monday morning, when all the guests arrive, at the right time for the dinner, the special dinner, serve people. Okay, that is a solution to what I call the bandwidth mismatch problem. So think about that. Think about that. I mean, what I'm really saying is that the rate of production here is very, very slow. But the rate of consumption is actually very, very, very fast indeed. 100 guests all eating their meals simultaneously. Each person takes about 20 minutes to eat that meal. But each meal takes 2 hours or so, or whatever I said, to prepare. So, okay, if I'm just duplicating what I've already said. If he produces a unit and C is not ready to consume it, maybe the producer should wait until C is ready, then P, and only then can P produce the next unit. But this time, this takes 10 units, so C will actually have to wait. I don't know. I mean, you can play around with these different rates of consumption and production and have a bit of fun and maybe explore some real life situations. Right, so I don't know what that scribble is. And what I'm actually thinking about is literally P is empty. Here we go. So why, but P fills the data. Look, P has actually put some data or food at the end of the buffer, and so on. He's put some more food here, more food here, more food. At this point, the buffer's full, but the consumer hasn't eaten anything. So there's a problem here because if the buffer hasn't got space for an additional meal or for additional data, what am I going to do with it? Am I going to lose it? I lost it? I got to remake that data, regenerate that data? Probably. So in this case, the buffer becomes full and the producer mustn't be allowed to put more data into it. That's a sort of safety consideration. All right, so hopefully, can you all see that really clearly? I mean, I've got a tiny little screen, so I can't really see it. I'll read it to you. Here's the producer program. Here's the producer. And the code for the producer is very simple, and I'll read it to you. So it's while forever. In other words, it's an endless loop, and you can always write an endless loop by saying while 1 equals 1, because 1 equals 1 is always true, and therefore the while loop will always execute again and again and again. But have a look at the first line. Now I'm performing a wait operation on a semaphore called buff semaphore. In other words, it's a semaphore governing access to the buffer. And before I say any more, I think it might be obvious to you all that it's unsafe to allow a producer and a consumer call simultaneous access to a buffer. Why? Well, supposing it's a meal, I'm just putting a meal in to the oven or whatever it is, or exchange plate or hot plate or whatever. And at the very same time, the client reaches out and grabs the meal. Well, anybody, it's anyone's guess what's going to happen to the meal. Is it destroyed? Does somebody get burned? Is the meal ruined? So it's unsafe to allow more than one producer, more than one consumer to access the buffer. So what I need to do to perform a wait on buffsum. Now initially, when you start the system up, buffsum is 1. In other words, it means that the producer, or it means that the consumer can access the buffer. That's supposing it's the producer that does the wait, and buffsum is equal to 1. So as we know from the definition of wait, the action wait simply takes buffsum and subtracts 1 from it. So it's now 0. And the brilliant thing about that is that it locks every other producer if there's more than one producer, and every consumer if perhaps there's more than one consumer. It locks them all out. I've got the exclusive right to access the buffer. And under those conditions, I'm going to put some data into the buffer. And maybe that takes a little bit of time to actually write the data into the buffer. When I've finished, I signal a second semaphore, not empty, and you'll understand why I've got a second semaphore here. Not empty is an indicator of whether or not the buffer's empty, literally empty. So if I signal not empty, maybe it was 0, maybe it was 1. The result of signaling the buffer is going to be 1, because we know, I think, that a buffer can only be in a 0 or 1 state. So if I signal a semaphore 3 times, it's going to end up being 1. All right, so you think a little bit about that. It's not very important. But finally, I signal buff semaphore. In other words, I change the value of buff semaphore from 0 to 1. And that means that if anyone else does a wait on this non-shareable resource, this logic non-shareable resource, the buffer, it's going to get access to it. Well, have a look at the consumer. And consumer is a process that is capable of infinite consumption of the data that I produce. So first of all, okay, logically, if you think about it, I'm going to perform a wait operation on the not empty semaphore. And the question here is the buffer empty or not? Well, let's supposing it is empty. I'll be waiting there for a while. If there's something in the semaphore, then I'm going to take the semaphore, which is 1, and decrease it by 1, so I can move on. And then, look what I'm doing here. I'm going to wait to get access to the buffer by means of looking at this semaphore. Either it's 1 or a 0. If it's 1, which we know it is, because there's a signal on that semaphore here, I can proceed. I can access the buffer. The wait operation results in changing the value of the buffer semaphore from 1 to 0. In other words, it's going to lock everything else out. I've got exclusive use to do what I want with the buffer for a short period of time. What I'm going to do is to take the data out of the buffer. And that takes a couple of, presumably it takes a little bit of time, maybe not a lot, but a little bit of time. And finally, so Hussein, okay, hopefully Hussein's back online now. So, okay, so the last thing I do, the last thing the consumer does is to signal the buff semaphore. I give up control you'll be able to convince yourself that not more than one producer can access the buffer at a given time. Not more than one consumer can access a buffer at a given time. And moreover, it's not possible for both the producer and consumer to access the buffer at the same time. And a little point, a little thing I've got to ask you is that if you've got to be a bit careful. If you swap these two lines around, you actually end up in deadlock. In other words, the producer can't produce, and the consumer can't consume. I mean, can I just very briefly explain this to you and why we get deadlock? Supposing we're looking at the consumer, and the consumer, instead of executing wait empty, is going to execute wait off semaphore. So let's supposing we get access, that we're executing this second red line, we get access to the buffer, and then I try executing wait not empty. But supposing the buffer is empty, in other words, there's nothing to take for me to take, I've got to wait. And if you think about it, if the buffer's empty and I've got control over the buffer, then the producer will never ever succeed in getting exclusive right to the buffer, because he's going to say, look, I'm trying to execute wait offset, but offset is 0, and I'm going to have to wait here because the consumer will never give up. Got the control of the buffer. It's not going to give up. It would only give up the right to the buffer if the buffer wasn't empty and the consumer could take data. But that'll never happen. The producer is locked out of being able to put data into the buffer because the producer can't access the buffer, can't get exclusive access to the buffer. So what I might ask you one day is, why does deadlock arise here? Why does it arise? If you're a bit careless in how you write these wait statements, you might get yourself into a bit of trouble. So you've got to be absolutely clear about what's happening. Right, so I made a note here, and it's simply, I want you to understand, at least I want you to understand why you need to take care, because I'm sure you understand why this might cause deadlock. In other words, both producer and consumer can't make any kind of progress. The producer can't produce and the consumer can't consume. And that is bad news. Right? In any system, if you can't get what you need, in other words, you're being starved of what you need, it's really bad news. I want to introduce a third requirement on this buffer problem. The producer should not be allowed to write to a full buffer. And to make life easy, we can imagine that instead of forget that. Forget that. Just imagine that the buffer is size 1, can just hold one item of data. And you might consider the following code for the producer. And it's exactly the same as the code I've shown you, but got a third semaphore called full, wait full. And I've got to wait until full is 1. And if full is 1, I can actually grab control over the buffer, put data in it, tell the consumer that it's now not empty because I've just put some data in, give up control, signal buffer, gives up control over the buffer, and I can get on with some more work to do. And here I'm some more work, and again I'm going to wait, make sure there's some space, and as soon as full is one, I can go ahead and etc. etc. I mean, the reality is that full here might not be binary semaphore. I mean, maybe it can contain values from 0 to some value of n to represent the size of the buffer, and every time the buffer's empty, it's going to, the value of weight is the value of full is going to be the size of the buffer. So I might have 10 spaces to put data in, and then it shrinks a little bit after I put some data in and so on. Okay, so can I just summarize that? Well, that's the corresponding bit of code for the consumer. Can I just draw some conclusions about the buffer to make a better sense of what's going on here? Firstly, I've guaranteed that you can use a buffer in mutual exclusion. Not more than one of the producer or the consumers can access the buffer at a given time. Secondly, the producer should not be allowed to write the full buffer. There's got to be space in it for it to write data. I mean, think about it. I mean, supposing, control center at NASA receives a message from a space vehicle with a vital bit of information, but unfortunately, there was no space in the buffer. The message is going to be lost, or the message is not going to be generated. But secondly, so the consumer mustn't attempt to take data from an empty buffer. I mean, what you might find in an empty buffer is absolute garbage. So you've just got to be very, very careful. Okay, so I think I'm coming to a conclusion. So summing all that up, 3 requirements. So have a look at those. Think about why we're bothering to deal with buffers in the first place. And so it's actually, technically it's a solution to the general producer-consumer problem. Because you might not just have a single producer, you might have 30 or 40. You might not have a single consumer, but you might have 50 or 60. And hopefully, if you choose the size of the buffer well, then you're going to smooth out rates of consumption and production. Sure, I wanted to stop here with it. Important result. Okay. I mean, the real life examples of this, you might have multiple threads, each wishing to write to the same pixel. You might have multiple processes wishing to put a job on the print queue. You might have 2 applications wishing to use the same user datagram port, internet communications. So this sort of problem occurs all over the place. Right? So another key thing that we've established here is a way of implementing asynchronous communication, because we know how to provide a mechanism for allowing 2 systems to communicate without performing any kind of synchronization handshake. In other words, the sender A doesn't have to wait until recipient B is ready to receive data. I just go ahead and transmit. And B doesn't have to wait until A has sent data. I mean, providing it has sent data in the past. mean, there is a bit of a problem because, as you know, I don't know whether you know what is meant by the ether, but it just means the vacuum of space. If you transmit an analog signal, there's no storage in the ether. But maybe if the receiver is ready, but it simply doesn't see the data because perhaps it was transmitted too quickly. And the idea is you're going to receive an analog signal, and you're going to translate the analog signal to a digital signal. But maybe the whole thing was just transmitted too quickly. The solution to the problem is to build a buffer. Build other electronics that is capable of receiving that sort of message. So I'll just temporarily finish there. What I probably should do now is to tell you a little bit about the coursework. Okay, so for those that weren't here right at the beginning, I'm going to issue a provisional document for the coursework on Saturday night, tonight, and I shall probably finalise it on Saturday or Sunday, so look at Moodle, because I'm going to put it up on Moodle. And let me show you the document. It's called Midterm Coursework. And as I said, it's worth 25% of all marks over the year. If you prefer, you can think of it as getting worth 50% of this term's work. And you'll have one more assessment, which I'll issue on the last teaching day. And I'm very generous. I will give you until the first day of teaching in 2021 to submit it. Midterm coursework, and I'll just show it you quite quickly, but you'll get an impression of what it's all about. Read it more carefully. I can't see that myself. Can you read that, guys? I suppose I could make that slightly bigger. Yeah, that's better. That's slightly better. So it's going to be released on the 30th, probably tonight. So where's D? This is useless. These are all questions. I'll try making it a whole page. Does that work any better? Press escape. Can't scroll down for some reason. Well, I can get part of question 1, and I guess it's to do with cache. If you add cache to a simple computer architecture, we studied in topic 1, the cache interface controller needs to be added to make the new system work. Briefly describe one or more functions the controller must perform to get the advantages of cache. So it's a cache question. And I'm sorry I can't show you the whole of the question, but you'll be able to have a look at it tonight anyway. Question 2a, show how a function f can be defined in Python to perform integer multiplication by using a while loop, and write a program to ask the user to input 2 numbers and then use the keyword print to display the result of calling a function. Like 10 marks, that's the half mark, and I'm so sorry, but I can't actually show you. No, I can't. Let me make it smaller. See if that works. No, I can't. This is dreadful. Yeah.
Mr. Chris, I'm sorry. Is it like a task that we have to do during the next week, or is it going to be a midterm test?
No. It's the midterm test. So I'm issuing it I'm giving you a provisional copy of the document tonight. You can have a look at it. If you have any comments, let me know. And I'll make a permanent, the final version available on Saturday or Sunday. So you need to look at Moodle in the next couple of days. But it's a written test. It's a written test. So you submit the results of this test, written test, in 3 weeks' time. Saturday. You have 21 days. 21 days to do it. Hassan. Sorry, repeat that, Hassan.
You can go ahead. I'm sorry to interrupt.
No, is that reasonable? 3 weeks. You've got a piece of work. It's got 4 questions, and I think I might add another one. But let me just sort this out. So I can't do anything here.
Mr. Chris, when is the actual midterm test? Or we have the whole period to do these function in it?
You're gonna have a look. You're gonna have a look at Python functions today. Yeah. Yes.
We're gonna attempt it today, or we're gonna have a look at it.
No, I'm gonna show you how to write a function in Python today, this afternoon. Yeah. But there's more.
Sure.
There's a bit more work to do. It's quite easy, and I think you'll appreciate that. And I'll give an example that I think is a pretty good solution to the problem I'm asking you. So I'm just getting rid of that. Upload a presentation. It's not coming out at all. So I think you best wait. And I might try again a bit later on just to show you it. I think I've got an alternative format that I can show you the paper. So let me remind you, it's 4, possibly 5 questions, and each question is split into 4 parts. Everything I'm asking you about is something that we've done in the course, or will have done by 4 o'clock this afternoon. Okay, so you don't need to look for books. Just, if you need to, just look at the work that the files that I've given you, or maybe some of the video clips I've given you to explain. Okay. So I think it's a fair exam, and I'm expecting around about 50 or 60 marks for a solid pass. Okay.
How long is the exam period?
I don't quite honestly know. Are you doing any exams?
No, but I'm just asking to
Well, I've decided to give you 3 weeks, and I think if you're doing physics, then the other Chris Gilbeck has actually started. I think he set the coursework. It's something to do with JavaScript.
Yeah, he gave us an assignment to do, but for your class, is it kind of an assignment and an assignment that will be marked on?
Oh yes, mine is assessed coursework, and you'll get feedback. Yeah?
Oh, so it's not an actual test that we have a time frame.
It depends what you mean by test. I'm asking you to go away, take it home, take this paper, look it up, and give me written answers to 4 questions, 4 or 5 questions.
That would be wonderful, really.
It is wonderful.
So much.
It
That's
is wonderful.
amazing, man. Oh, that's really cool.
It takes a lot of pressure off you. On the other hand, I think you're going to have to read what I've given you. Some of the material I've given you, you must read it, and you must, if you have great difficulties, you can always ask me to clarify what I want. But,
Sure.
Okay, so I'm trying to make this assessed coursework very fair. Okay.
You did. Thank you so much, sir.
My pleasure. My pleasure. Right, we're going to carry on at high speed, I think. So I'm going to upload another presentation, and this time, okay. So this is what I meant earlier on. I'm going to show you two short presentations which involve a single diagram. I just want to quickly explain these two diagrams. So first of all, I'm going to give you, oh, where is it? Wait a minute, I've got to look back. So it's this, right? So I'm going to try and explain something that's quite important that I haven't spoken about before. So, where are you? Where is it? Where is my presentation? Upload a presentation, let's see. So I'm confirming. Oh dear, it takes ages to do these things. But hopefully it's on its way. I mean, it might be me that needs to log out again and try again. So I'm not being allowed to load my presentation. So no, this is not good. So guys, I'm going to log out. It'll take me a couple of minutes to log back in again. Okay. Okay, so I am logging and will log back in. I'm going to pause the recording. Sorry, so this is going to be a gap, little bit of gap in there. So, sequence of events of the full handshake, just to repeat myself, the send array senses that the receiver B still is not acknowledging the previous request, therefore the request is continued. In other words, I extend my hand to keep it up until you do see it. And eventually device B will sense the request and sends me an acknowledgement. Receipt, it acknowledges the receipt of the request, so it's seen my request, and B extends its hand, as it were, for the time being. Okay, so device A now senses B's acknowledgement, and A drops its wrist, and A drops its hand. And finally, B senses A has sensed B's act, so B drops its act. So, you know, this is just formalizing what I've just told you about those waveforms. So, I want you to pay some attention to what I've got to show you now, because it's quite important. I've got two flow diagrams, one on the left, one on the right, and I've got machine A. The first one is machine A, and it's just got two states, two state boxes, and I've got machine B, which has got three state boxes, and we're talking about synchronization between these two machines, and I'll explain what I'm talking about. Machine A wants machine B to perform an action on its behalf, and it's very important that B sees this request. Have a look here. This is a state box, and I'm outputting a request signal. Request equals 1, sending 1 to this machine. And machine B is monitoring what it sees in its decision box. request being 1, in other words, the request equals 0, it's just going to wait. It's going to wait, and it's going to wait until it does actually see request equals B1. And the reason why B might not see A is because machine A might be very much faster than machine B. And I want to explain how that situation arises, namely that one machine doesn't see a signal that the other machine sent it. I'll spend a few minutes just talking about that a bit later on. So let's explore the logic of these two machines. We've got two machines talking to one another, and I want to make sure that machine B will see the request signal from machine A. The reason being, for sending machine B the signal, that it wants machine B to do something on its behalf. So if I keep sending the B out, eventually this machine B, will actually see request equals 1. So it's going to change state here, and it's going to send an acknowledge signal. So I'm assuming that this machine is still sending out a logic request equals 1 signal. So this is going to be picked up in this state box. So we're in this state now. What I'm going to do is to send out an acknowledgement to this state box here, and send out an acknowledgement to this state box here. And if request equals 1, I'm just going to loop around, just wait in this state. I'm going to continue sending the acknowledge signal again and again until this machine has left this state. In other words, I leave this state, request becomes this request becomes let me see, request becomes 1, I think that's right. Now I've got to work this out on the fly a little bit. So I'm sending acknowledgement to request. Okay, so as soon as this machine sees, by means of its decision box, that it's received an ACK equals 1 system, the machine will change states and go into this state. And what it's actually going to do is, whilst ACK is 1, it's going to see that ACK is 1 using this decision box. It's going to just stay in this state, do nothing. It's just going to stay in that state. So on this side, eventually, because we've changed from this state to that state, we're not sending out request equals 1 anymore. And this decision box will actually determine that the request signal is now 0. So we're going to change state here and do something, maybe the action that's required by machine A. And so what's actually going to happen is that because we're sending out 1 here, and the machine will loop back if ACK is 1, it's actually going to change state, some other state, and ACK becomes 0. So ACK becomes 0, and since ACK is now 0, we're going to change state here. So I reckon that this is as complicated as what I call communicating state machines gets, because we really don't know how fast either machine is, but I can guarantee that if machine A is faster than machine B, then machine B will actually get to see eventually this request, and then it'll, at this point in time, it'll send an ACK out. And eventually, because I'm continuing to send an ACK to this machine, it's like, you know, keeping my arm up, this machine will actually see see ACK equals 1, and it'll change state here. And in this state, it's going to see that ACK is still 1 and loop round. And because this machine's changed from this state to that machine, at this state, request becomes 0, and I'm going to change that again. So the idea here is I'm trying to formalize you getting me to, I'm sorry, I'll say that again. I'm showing this diagram because it formalizes the idea that I'm going to keep my arm up until you see it, and you raise your arm, and you're going to keep your arm raised until you see me drop my arm, and in which case you're going to drop your arm. So you could translate that in terms of requests and acknowledgements. And what we're talking about are serial machines, communicating serial machines. Each machine passes through its states in serial fashion, and including this one, machine B. But at this point, I'm calling on this machine to do something on my behalf. I'm sending it a request. It's waiting for a request here, because whilst request is 0, it's just going to stay in this state. And then when it sees my arm lifted, it's going to raise its arm by sending an ACK back. And eventually, I will lower my arm. In other words, request becomes 0, and I change state here. So this, you know, it needs a bit of time just to read through and digest all this. And I've got a little note on that effect. And one other little computing challenge I'd like to give you is what happens if you want 2 machines to start at exactly the same time. And the condition is that both machines are clocked with the same clock. In other words, there's no problem of one machine being very, very fast and the other relatively slower. Well, I'll just offer you this diagram, which is contrary to my use of state diagrams. It's using just a simple state diagram. So it's not using state charts, it's using state diagram. Got 2 machines, A and B, and whilst not A, so I've got an input A, whilst it's the case that not A stay in state B. And however, when I do get an A signal, I can change from this state into that state. And likewise, this state is actually waiting for B to change from a 1 to a 0. So if B sends a signal, while not B is the case, I'm staying in that state. So if B, not B is true, right, I'm going to change state. So machine A here is sending this machine signal to start going, and at the same time that this machine is telling this machine to start going. So we want to synchronize start. Okay, so you might want to think about this. Life can become a bit complicated, especially if we don't know how fast one machine is with respect to the other. You probably do need a third machine to arbitrate between the starting of the machine on the left and the machine on the right. And I'm just going to end this part of the presentation with a little thought, is that very often we do need to use signals, like we send a request and we know that the request is being dealt with because we receive an ACK. And the question is, are there any situations where such schemes cannot be used? Or are there any schemes that don't involve sending a request and an ACK? And the answer is certainly yes. And just for want of a mentioning the schemes, autosynchronous encoding, putting things very, very simply, I don't think I've got any more slides here, have I? I've got lots of slides here, but I won't go through these. The key idea is that I can send you data and I can tell you how to verify that what you've actually received is valid data. And as soon as you receive valid data, you can go ahead and process it and send me the result back. I don't need a request, and I don't need an ACK. And the reason for that is that a slight trick, because I can actually send you one bit of information using 2 bits. And when you've received, say on a bus, exactly n bits of valid data, you can assume that what I've actually sent you is a valid word. Start proceeding. Because there's no need for a separate request, a separate acknowledgement of that. I know that if I send you some data which is auto-synchronously encoded, that you yourself can test it for validity. I mean, typically, I'm only going to send you a request after I know that all the data on the bus has actually settled and is valid. You know, maybe a little bit of time after I put the data on the bus, I send you a request, and so on. So I hope you've coming away with a couple of ideas and about synchronization and signaling schemes and the way in which you can represent that. I hope you've learned something new here, or you can think about these new ideas. But I haven't finished yet, and I'm just going to have to let's see, just going to have to check time. So it's coming up to about 3 London time, and I guess some material I had in mind to give you will have to be given to you at a bit of a later date. So what I'm going to do is to immediately start on a Python session. So here we go. The file's being converted. Just a couple of minutes. The pages are being processed. And we'll just spend half an hour on this, but I do want to fulfill my promise of actually showing you how you can define function to multiply two numbers, which involves using a while loop. So I'll show you how to do that. And if I've made any mistakes, you can correct them and try running the program, making sure it does do. I suppose say it's done. So I'm stuck on processing page 12 of 23 for some reason. Brilliant. 13 of 23. 14, so it's really very slow system we've got here. I apologise for the slowness of things. 15, nearly there. 16. 17, crikey, yeah, 17, 18, 19. I hope the system doesn't crash. This usually doesn't take this length of time. 19, nearly there. 20. 21. It's just an ordinary PDF, it's nothing special, but it's taking a long time to process. Right, so I'm going to cover the first part fairly rapidly because I want to home in on how you can define a function in Python. So here we go. So what we've done so far, we've looked at while loops and for loops, and we should know how to write some do some programming using both kinds of loop, and maybe we should know when to use either type, and forget the next, because I haven't looked at bisecting examples. Today I'm going to briefly describe the need to structure our programs in order to hide all the horrible detail of hundreds of lines of code, perhaps. Specifically, I'm going to have a look at functions and how to specify a function. And finally, which will take just a minute or two, is to know when to use a return statement versus a print statement. So we've learned how to use a print statement. It displays the value, typically a value of a variable or an application function application. So there's no difficulty there. So how do we write code? Well, we've covered a few language mechanisms. I mean, we know how to deal with a string, or we know how we can compare to scalar numbers and so on and so on. And so what else do we need to know from this list of points? Well, okay, we don't have to do any more work in order to write very small scale problems. You know, it's like code which is up to about 25 lines of Python and so on. But when we start to write projects or larger programs, I mean, maybe I'm going to work on a program that calculates the action which results from reading in 20 different sensors, or maybe I'm writing code to produce a Python editor so I can do some nice word processing, that has become very different. And what I need to do is to make sure I can keep track of all the important details of the code I've written, and I know where the important parts of the code are, and how do I know that the right information is being supplied to the right part of code. I mean, in other words, it would be very nice if I can split code up into specialized units, where for each specialized unit I know exactly what input it takes and what output it should give. And it would be very nice if I could actually design the code in such that all the details, all the lines of code are somehow hidden from me, or hidden from the user of that code. Well, a lot of code isn't a good idea. In fact, it's a virtue if you write small amounts of good quality, well-documented program, and you've specified the functionality of each piece of code accurately. And it's at this point that we can introduce Hassan. Radban, Mr. Radban, are you here? You okay? And, okay. So I need to. It's at this point that I'm going to introduce functions, and it is, after all, a mechanism where I can split code up into component parts and tell you in an abstract form what this block of code does. Okay, so two things: decomposition of a lot of code, a lot of program code, and I can actually describe a function to, for example, send a data packet out on the internet without messing you, without bothering you with all the detail at all. So we should all know what. I'm going to skip this. It's just a little example of constructing a projector for the Olympic Games out of, say, 100 smaller projector modules. So just moving on. The idea is that I want, whenever I write a substantial amount of code, for the code to be more or less self-contained. I want to break up code into simpler components. I want each block to be aimed and reusable. And I want to keep code organized. And I want to keep the code coherent. I just want code, a block of code, perhaps just to do one main thing, not 6 different things. So we can achieve decomposition with functions, and a bit later on we're going to use classes, so that's another big step to take. So I want a way of suppressing detail using abstraction, and I can achieve abstraction with function specifications or documented text as part of the function. So to get abstraction, and what I mean by abstraction is just simplification, and I can simplify 50,000 lines of code by saying, is this as easy as that? I think I've told you the fact that I think Windows 10 code runs to something like 25 million lines of code, and it's very, very modularized. It is broken up into identifiable blocks, and each block having a particular function does something very specific. So what we can do is to write reusable pieces of code, and these are called functions. You don't run a function. What you do is, as part of a program, you call or invoke a particular function to perform its function within a program. So some characteristics of a function. Has a name, it's important, you can name a function. Has 0 or more parameters. It contains its own documentation inside a function definition. It has a body, a well-defined body into which you put all the functional code. And finally, a function will return a value, return something. So this is the key part of a function. It returns a value. Think of the square root function applied to the integer 9. It's going to return a value. What value? The square root of 9, which is 3. Returns a value, whatever it is. Think of a little function that tests any given number, whether it's odd or even, and it's going to return a Boolean value. Going to return Boolean value, meaning whether a particular number is odd or even. So that's quite straightforward from the maths that we're already familiar with. So here we go. This is the main piece of this part of the presentation. This is how you write a function, and this is how you call or invoke a function. Alright, so to invoke a function, all you do is to write the function name, supply 0 or more parameters. Since it returns a value, you can assign that value to an appropriate variable. So have a look at this. Have a look at this very simple function, and it's given us a name. Is either. That's the name of the function, and it comes after the keyword def, short for obviously definition. Def is even, and this is followed by 0 or more parameters. It doesn't have to have parameters. It could have 0 parameters. But this one's got 1 parameter, and it's the, I guess, according to the documentation for the function, I is going to be a positive integer. So inside these triple quotation marks, you get a description of the function. What does it do? Well, it takes an input, which is an integer, and it returns a truth value. True if I is even, otherwise false. And I've got okay, so here's the body. So immediately after the documentation section comes the body. It's not marked physically. It'll be marked indentation of text. I've got two statements, two Python statements. Print something like is even, it's active, and I'm running inside a function. And finally, I want to return the Boolean value of the remainder of I being divided by 2 equals 0. Okay, so if you now run the program, so this is what I meant by saying that a function can be invoked. You simply write the function name together with a parameter, and the parameter is 3, and it'll return. This will return either true or false. So try it. And you might want to try what happens if you print is even 5 to 3. Is there any difference? You get the same result. Okay, so what you should get is simply, I don't know, just adding unnecessary detail here. Here is the body of the function, in the function body. This is the function body. As I said, it comes after the documentation section. And it's quite nice to be able to document your your function. I mean, it's very helpful, especially if it's a very complicated function, very specialist function, but only you as the specialist really understand what it does. I mean, it's nice to be able to make it clear what functionality, what the function does. So just a couple of other notes. And talking about the variable scope, I mean, the formal parameter in a function, that's a formal parameter occurring within the body of the function is going to get bound to the actual parameter when you call the function. So, for example, if the actual parameter I give to the is even function is 12, 12 is actually going to be bound to the formal parameter x, and what's being bound is the actual parameter 12. Okay. So, looking at this little function, f, what I'm doing is to, first of all, take the formal parameter and add 1 to it, and then return the value. So, if I assign 3 to the variable x, and I can plug x into f, this expression f of x, the value of x is going to be 3, and I'm assigning the result, and I return x, which hopefully should be 4. I'm assigning the value 4 to the integer variable z, so z equals 4. So a couple of notes here. This is the function definition. This is running the program by, first of all, defining the formal variable and by defining the actual parameter and then plugging in the actual parameter into the function itself. So I'm applying f to 3, and assigning the result to z. So I'll leave you to read on here, but what I'd like you to do, and I hope I can trust you to all do this, is just cut and paste these, or look at the Python program I've given you and run them in Python. Just get used to what's happening. If there's no return statement, and when you run the program, it's going to output something like no value, okay? Or none. Python will return the value none if there's no return statement given. It represents the absence of a value, so it's very peculiar, and it's probably a mistake that you didn't return something. Difference between return and print. Return only has meaning inside a function body, and only one return can be executed within a function. And the code inside a function, but after a return statement is not executed. So if you've got code after the return statement, it can be ignored. A return statement has value associated with it, and it will be presented back to the caller of the function. So a print statement can be used outside functions, like I can print the value of the function f applied to 3. Can execute many print statements inside a function if you want to. If you're debugging a function and you want to know what's happening where, you can use one or more print statements inside the body of a function. And code inside a function can be executed after a print statement. So if you want more code after a print statement, no problems. And a print statement has value associated with it because that value is going to be out to the console, to your screen. But it's quite unlike the value returned by a return statement. And so I'm going to leave you with this thought, because I don't want to, we might return to this a bit later on in the term. Here I've got a function, this has a print statement, doesn't return a value. Here I've got a function that has a print statement, but it will return a value, y. Here I've got a function, cz, which returns a function, z. It returns z. Z here is going to be a function. It's going to return the function. So what I could do, I could apply in a function c, which is this, in the function a. So you can apply one function to another function. See what happens. Just try this out. Learn a little bit about what Python does. And I want you to, in your own time, I'm not going to explain this, is to look at the problem of scope and just read the notes and maybe try these different programs out. You've got 3 programs here. And if you don't understand the result, like for example, why you get I think you get a problem with this one, just let me know. Right, and so I think finally, so I've got a really quite hard. Okay, so just to test your own selves, look at this program here and try and make some sense of it. Why do you get this? Why do you get the result you do? Just explain this. Right, so it's gone 3:45, and I did promise I'm finishing here. And you've got these notes, and I think you've got all the programs in a Python file that I've mentioned. So you've got a bit of time to spare over the next 3 weeks, hopefully. Not going to be overloaded with coursework. I hope you give a lot of attention to my coursework and do lots of reading and lots of thinking. But as I said a while ago, I'm going to try and show you, let me see, I'm going to try and show you way in which you can, try and show you how to perform a multiplication using a function. And what that involves is writing a little bit of code up wrap it up inside a function and deal with it. So here we are, that's all I'm just about to. Here we go. So it's a PDF file, upload that, just 1 page, won't take next to no time. If it appears, that is. So I'm not sure why it has not been successful. Let's go back to upload the presentation. Oh, okay, it needs me to confirm something. Oh dear, let me try again, 3rd time. Upload a presentation. So I'm going to consign the last presentation to dustbin, and I'm confirming. Still hasn't arrived. So please bear with me. I'll do my best to. waiting for it to be uploaded, even though it's a one-page document. What I could try and do is to share my screen and show you what I've got here. So let me temporarily close things down and so I'm sorry to keep you waiting. Determined to find a way of showing you the file. Really there, I think. Right, I'm going to try and share my screen, so I'll see if that's worked. I'm showing my screen and want to. This is it. So it's probably. You know, I hope you're not disappointed in seeing this. I've just got to get rid of this now. So hopefully you can see this. And oh dear. Okay, so if you can't see this, I'll read it out to you. I can make my screen a bit bigger. Hopefully you can see that. So here we go. We're looking to define a function that multiplies two numbers. I've got two parameters, m and number. So the idea is that I want to multiply m by number. So first of all, I declare two variables, ac, which is assigned the value which I've just put in, m, that's the first number. I'm setting count to be 0, and I'm putting number as the limit number on the loop. So whilst counter, which is currently 0, is less than number, and I'm going to perhaps put in 10 here. So I repeatedly go around this loop, and I'm going to increment variable ac, which currently is m, by n, and then I'm going to increment counter by 1. So second time around the loop, I'm going to got m here, so I'm adding so I should really, okay, so this n should be ac. No, it shouldn't be ac. I'm accumulating a value. Initially ac is m, and then I'm repeatedly adding a number to that. So I'm sorry, the logic has failed a little bit, but I'm repeatedly going round the loop, and the idea is that what I want to do is to add m to accumulator number times. So if m might be 5, number might be 10. So what I'm looking to do is to multiply 5 by 10. So initially, accumulator is m, And what I want to do is to repeatedly add m. Okay, so the n should be an n. Number of times. That's 10 times. Starting with counter is 0. Okay, so that nearly does the job. And what I haven't done is to respect the rules on indentation. Each of these lines should be indented by 2 spaces. Okay. This is fine. I haven't put any documentation in. So that's the answer. The question to prediction that I stated. So I'm stopping sharing this. So hopefully you can get a copy of this from the recording if you want. Okay, so I'm stopping sharing my screen. And that, gentlemen, is about as much as I can give you today. So I hope you've learned lots, or at least, hopefully, you're stimulated into thinking about one or more topics I have covered. And so the score at the moment is that I shall place a copy of the document that I've shown you already in part up on Moodle tonight. It's provisional, and it might well change a little bit, or a lot, by Saturday night. So I'll aim at releasing it, the non-provisional version on Saturday. And you have 3 weeks and a day to complete that. So it'll be on the Monday, 3 weeks later. Yeah? So I've tried my best. We've had a lot of material. But fortunately, the system didn't break completely halfway through, as it usually does. So you take care of yourselves. I hope you can hear me. Nobody's... Perhaps you're all asleep, I don't know. So...
I have a question.
Please go ahead. Ask.
So the exam is that you will have 3 weeks to make the
three weeks.
Exam.
3 weeks. It's not an exam. It's an assessed coursework, written coursework. It's not an exam. Okay, you've got something like 4 questions, each worth 20 marks. You do it at home. You don't do it online or anything. Okay.
Yeah, that will not be a problem. Thank you, Mr. Chris.
So I hope excellent results. And I realise this session's been a bit tricky because I've been sort of moving from synchronisation to mutual exclusion to semaphores. But these topics are all interrelated. And it'd give me great delight if you can master some of these basic concepts. Basic but very important concepts. Okay, so I look forward to seeing you in 2 weeks' time. Yes?
Sir, is there any assignments that we have to do over the midterm apart from?
Who's talking?
Farhat.
Oh, Farhat. Okay. So ask the question again, because I don't think you were here right at the beginning, were you?
No, I couldn't connect in the beginning. I was having problems with my connection.
Oh, okay. So what I'm doing this is worth 50% of this term's work. So it's the midterm assessment, and I'm asking 4 questions. Every of those 4 questions are based on work we've done, very closely based. For example, the Python question I've just virtually solved for you, so I might change it a little bit. But every question I'm asking is based on work we've done or some of the videos. And I did actually remark that relatively few people have looked at the recordings or the video clips I've made on YouTube. but everything's there. Okay, and if you want to, if you run into any problems or you have any questions, let me know either by email or you can request I think you should be able to request an online session for half an hour this time next week or something along those lines. It's up to you to decide what you want. Okay, does that help?
Yeah. But is it not required for us to get the recommended course book as well, or is it just rely on sources on notes?
Well, I've photocopied about 8 pages from the recommended book, and that appears in topic 1. And it might be useful for you to get that book for background, but for this assessment, you just need my notes. Honestly, okay. So enjoy it. Enjoy the challenge. Good luck to you, and keep well.
You too.
Okay, thank you. So goodbye, everybody.
Thank you.
Thank you.